In the previous video, we learned a little bit about what an algorithm was and its benefits and why we should really develop our algorithmic skills. But it's still a pretty large jump from knowing what an algorithm is to knowing how to write a good algorithm. So before we get into the details and the methods of how to write a good algorithm, we want to take the time to look at a couple algorithms. And so in this video, we're going to go through a couple different algorithms, kind of break it apart, and talk about the process. What are some good things? What are some bad things? And see what some good algorithms should look like so you kind of have a vision or a goal in your mind of when you're developing your own algorithm, you kind of already know what good algorithms look like. Ultimately, what we want to do is train ourselves to start thinking algorithmically. So the best place to start is by looking at other algorithms that are already working and start breaking those down to see what are the good qualities of these. And then in a later video, we're going to start seeing, well, how do we actually develop these algorithms? So let's start off with linear search. So in linear search, what we want to do is, given a list of numbers, find if a number exists or not. So that's the problem we're trying to solve. So the input to this problem might be the unordered list L of n numbers, and k being the target number. The output of this might be true if k is found in L, false otherwise. So this is the basic description of the problem. This is what we're trying to understand first, is what are we trying to do? And once we can understand the inputs and the outputs and any assumptions we might be making or might not be making, then we can start thinking about, okay, what are the steps to solving this problem? Okay, so now that we have an understanding of the problem, we know what our inputs are, we know what our outputs are. Now let's try to figure out how we want to do this. So before I show you any of the algorithm, let's just kind of think through it on a whiteboard. Like if I were talking to somebody, how would we walk through it? Well, simply we would look at the first number. Does it equal k? No. Okay, let's go to the second number. Does it equal k? No. Okay, let's go to the third number. Does it equal k? Nope. And you keep going until either you find something that equals k, therefore you would return true, or you get to the end of the list. And if you exhausted all the numbers and none of them have equaled k, then you know you can return false. So in order to keep track of where we are, we might want a variable that we're identifying as I, and we're going to start 0. Now in computer science, we typically start counting at 0, not at 1. That's why I'm using that here. If you haven't taken an intro course yet, once you start watching some of the intro videos, it'll make a little bit more sense. I'm not going to address that here. So while I is less than n, so basically we're going from 0 to the end of the list. So we're going to keep looping until we've checked every number. And so if L at I, so if at that location in the list, if it's equal to k, we want to return true. Else, we want to increase our pointer or our counter where we are in the list. We want to go to the next element in the list, and we keep going. And then if we make it to the end of the list without returning true, we know that we can return false. So this is linear search. But as we did in the previous video, we didn't just stop here. We walked through a couple examples. So let's do that now. All right, so let's use this list as an example. 1, 2, 3, 4, 5. It doesn't have to be sorted, but this will be just fine. And the value that we're going to look for first will be 5. So we know that the result from this algorithm should be true. So the first thing we want to do is set I to be 0. And then we want to say, well, I is less than n. Well, we know n is 5 because there's 5 elements in the list. So 0 is less than 5. That's true. So now we want to check if L at 0, or the first element in the list, is equal to k. It's not. So we're going to increment I to be 1. And so that means we're going to be checking, is 2 equal to k? It's not. So we're going to increment to 2. And we're going to keep checking until we get to the last element where 5 is equal to 5. And so we're going to return true. So that works. So now let's say k is 6, meaning we should return false. So again, I starts off at 0, and we check 1 against 6. That's false, so we increment I to 1. We check 2 against 6, that's false. 3 against 6, 4, 5, Again, all of these are false. So then we get to the end of the list where I is now incremented to 5. 5 is not less than 5, so that becomes false. Then we jump down to step 3, meaning we return false, and that is the correct behavior. Okay, so we want to think a little bit more now that we kind of proved that the base case of it does exist, we were able to find it. It doesn't exist, we weren't able to find it. Now we need to think a little bit about the boundaries. So does it matter that the list is empty? So what would happen if we had an empty list? So I'm just going to do basic set notation here for empty list. So n would then equal to 0. So let's walk through our algorithm and see if our algorithm can handle this input. So we set I to be 0. And now we're checking to see if I is less than n. Just like 5 was not less than 5, 0 is not less than 0, so this would become false, and we return false. And that's true because there are no values in here, so it doesn't matter what k is. K could be 8, k could be 1. It will never be in the list, so we should return false. So we know that this linear search algorithm is working pretty well. Okay, so the next algorithm I want to look at is bubble sort. Now, bubble sort is one of those standard sorting algorithms that many of you will see in your intro courses, and it's a good sort to start with. Now, with any type of sorting algorithm, what we're trying to do is, given some list of numbers, we want to sort them in some order. And in this particular example, we want to sort them from minimum to maximum. So we need to ask ourselves, what are the inputs to this problem? Well, it's simply an unordered list of n numbers. Okay. What are the outputs? Well, we want L to be in an ascending order. Now, you might make an argument, well, that's not really an output since we've already been given L. You can make that argument. Maybe there are no outputs in this particular example, but I'm going to set it up in this way. We'll see different formats as we go throughout the videos of expressing what our inputs and our outputs are. But for now, we'll just assume that our input is an unordered list of numbers, and our output is that list, but in ascending order. All right, so as we did with the linear search, with bubble sort, we want to go through and see what the actual algorithmic steps are. But instead of just showing you the steps and walking you through it, let's walk through it first and see kind of the process that we would normally take. Because when you're approaching a new problem, you don't automatically have those steps. You have to kind of walk through and figure it out. So that's what we're going to do now. Let's start off with a very simple example where we have just one element out of place of the list. So let's go 2, 1, 3, 4, and 5. So we know that ultimately we want 1, 2, 3, 4, 5. So how are we going to do this? Well, if we go through and we just check these first two elements, are they in place? Meaning, is the left element less than the right element? We're going to know that they aren't. So let's go ahead and swap these two elements. So then we end up getting a list that's 1, 2, 3, 4, 5. So then we want to check, are these two elements out of place? Because yes, we're looking at this, and as a human, you go, oh, well, we're sorted, we're done. But we can't look at the whole list at one time. We have to look at these pairs. So let's look at these two elements. Are they in sorted order? They are. So now we want to look at these two pairs. They're in sorted order. Now we want to look at these two pairs, and they are in sorted order. But we're not quite done. We want to go back through the list to make sure that we truly are sorted and making sure that we didn't do any swaps. Because until we don't do any swaps when we pass through the list, that's the only time that we know that we're truly sorted. So we would loop through it one more time and see that we are sorted. So let's look at a slightly different example. I'm going to get a sorted order, but from max to min. And I'm only going to do 3 elements just to save us a little bit of time here in the video. But the first step would be to check, is 4 and 5 sorted? They're not, so we're going to swap them. So then we get a list that looks like this. And now we want to check, are 5 and 3 sorted? They're not, so we're going to swap them. Then our list becomes 3, 5. And now we want to check 4 and 3. Since we got to the end of the list, we want to start over and keep going until we have no more swaps. So let's check 4 and 3. They're not, so we have to swap 3 and 4. 4 and 5 are not, so we're good. We then go back at the beginning. We walk all the way through the list. We see that we're not performing any swaps. So we say now the list is in sorted order. This is the basics of bubble sort. Now that we've walked through the steps, let's take a look at what an algorithm form of this might look like. So here we want to repeat until we haven't performed swap. So basically we want to keep going through until there has been no swap. So we have a variable called swap. We're going to set it to false. And then again, we want to loop from the beginning of the list to the end of the list. And we want to see if L at I minus 1 is greater than L at I, meaning they're out of place. So if they're out of place, we will then swap those two elements. We'll set swap to true. And because there was a swap, we're going to repeat from B back down. Okay, so we'll keep repeating all of that, or excuse me, from A back down. And so we're going to keep repeating that until no swap occurred, and then we can exit. Okay, and again, I'm trying to show you different ways of expressing algorithms because there isn't one way to do it. Now, one thing I want to point out is this function that we use called swap. Now, we haven't defined what swap is, but swap is pretty straightforward. You take this one and you replace it with that one. If it's a function or a utility that is well known and easily implementable, then you don't need to truly define it. So something like this is okay. Now that we've kind of seen this and we've seen linear search, we're ready to start thinking about how do we end up writing good algorithms, and that will be in the next video. The last bit of information I want to leave you with is that good writers will constantly be reading other work to get inspiration, to see different styles, to influence their work in different ways, learning what not to do, what they like, what they don't like. Good computer scientists do the same. So it's really important for you to get out there and look at different algorithms. So maybe you are researching bubble sort and you see something called insertion sort. Have a look at it. See how it's built. What are they trying to solve? How are they trying to solve it? Because you never know when something you've read earlier is going to influence what you're trying to do today. So the more you go out there and you practice your algorithms, you read other algorithms, you study other algorithms, the easier this will become.